So we're gonna go over the lathe section of this. Like I said earlier, you know, if the part doesn't have chamfers on it, you know, just put like a 10,000 chamfer on there. Unless otherwise specified, you know. And that just helps smooth the part, so you know you reduce any kind of burr that's on the corner. Alright, so we got this part. It's going to be right on the lathe. So I'm going to go to manufacture. And once I'm in the manufacture mode, I'm going to go to setup. And I'm going to tell the software that I'm cutting it on a lathe. So it's going to be this turning. So where it says turning or mill turn, what they're calling mill turn is basically a lathe with live tooling. Because just keep in mind, some lathes have mill functions. You know, they have like a C or Y axis mill capabilities. And similar to the video we watched last class. So I'm gonna put it on turning, and I would suggest, you know, not everybody does it this way, but I think it's the easiest way to do it. And that's to put your stock, put your origin, not on the stock front, because you look right now, the Z0 is on the tip of the stock. Put it on the model front, okay? If you have to do any kind of editing on the program, that makes things way easier. Also, when you're setting the machine up and running your first initial part, it's really helpful to have your Z0 on the face of the part, because when you're watching your distance to go and watching the tool, make sure, you know, it looks like it's going that distance, you know, it just makes things a lot simpler. You know, like say that you have to turn back a 1/4 inch, right? So if you look at the program, and it says that it's turning back Z minus 0.25, and you're watching your distance to go, and it's telling you that, you know, once you get to Z minus 0.25, that, you know, that you don't have to go any further. It's going to go up this shoulder and then down this nose. It's just a lot simpler. I would think that Fusion would have that by default, but I guess not everybody uses their lathe like that. I don't know. It seems to make more sense to me to use a lathe, you know, where the Z0 is on the face of the part. Okay, so I'm going to go to my stock tab. I'm going to put it on fixed size cylinder. And the reason why I'm doing that is because if you use relative size cylinder, the first face pass and the OD pass, it may try to take too much material off. So you probably don't want to use like a radial, like a relative size. I would definitely put it on fixed size. And the OD is going to be 1 inch, which I'm assuming you are using 1 inch material on that. Are y'all cutting this to length, or are y'all gonna part it off on the lathe? Yeah, parting it off is probably the best way to do it. Now, when you first start running the lathe, you know, it may be more troublesome trying to get that part off tool set and working right, but it's relatively simple, really. It's actually easier to just part it off. But what I would do is, I'm not sure what the through spindle bore size is on the lathe, but let's say our part's 20 inches, our stock's 20 inches long, so you have like a 20-inch piece of material. Now it looks funny on the setup preview, That's because I have to change this model position to be from the front. But we want to give ourselves some material to face off. Because right now, there wouldn't really be anything to face off. So I would put like 50 or 100 thousandths. 50,000 is probably good. So it's gonna look something. Yes. Well, the part off tool would cut it. Yeah. So what you would do is you would face it, turn VOD, and the part off tool is gonna part it off to the right length. And I'll show you what I mean in just a minute. Okay, so first thing I'm gonna do is I'm gonna go to face, and I don't know what y'all's maximum RPM is on that lathe, but yeah, I mean you're cutting aluminum, so we'll go maximum 3,500. That might be a little fast. Yeah, we'll just put it at 3,000. And I would always use feed per revolution. I mean, by default, that should be checked, but it's not. But you're pretty much always going to have your feed rate per revolution on a lathe, unless you're like cutting plastic. If you can just go maximum RPM at all times. And because our feed per revolution, I guess it would help select the tool first. So I'm going to go to my Lathe Tools. If you don't have any Lathe Tools, you can save it to the library, or you could use one of their tools they have pre-made. Some of their tools are kind of questionable, really. Really, if I was y'all, I would create a folder, one for Lathe Tools, like where you create a new library. And I would make one for Lathe Tools and one for mill. And that's just what I would do. You can even do them for like family of parts, or like for materials, like mill aluminum, because the tools you use on aluminum may be a lot different than the tools you use on steel, and you may want to keep them separate. But I'm just gonna go ahead and create a tool. I already have some created, but just to go over how to make a tool. So anytime that you want to make a tool, the first thing you need to do is give it a place to save it, a location. So it could be a folder, it could be the job. Right here where it says documents, this is the name of the file we're working on, right? So it would save that tool to this file. The problem with that is once you open up a different file, that tool's not going to be available. So it's up to you. But because I already have an OD tool and a face and OD tool, I really don't need to create more. I'm just going through the steps so y'all can, so y'all know how to create y'all's tools. But anyway, so in that case, I'm gonna select the document. But if I was y'all, I would just save it to the library or create a folder and name it Lathe Tools. Okay, but I already have those tools, so just for the purpose of, you know, showing y'all, I'm gonna select this the document, okay, and that's the file I'm working on. Okay, it's saved as advanced 201 lathe. Okay, so in that case, I'm gonna to create the tool, I'm gonna go to this plus sign, and remember that plus sign is grayed out. That's because you haven't selected a location to add a tool to, like when I say a location, like one of these libraries or subfolders. Alright, so I'm going to click the plus sign, and the software wants me to tell it what kind of tool I'm going to make. So I'm going to make a turning general tool. And you really only have to do this one time. So if you already did it, you know, just ignore this. Let's see, face and OD. Turning tool. You can even put like the insert radius. Like sometimes what I like to do is I'll put TNR 0.015. That would mean tool nose radius. So it had basically it has a 15,000 tool nose radius. But that's because I use dedicated tools. Like, you know, I'll have a face and OD tool, and for that tool number that I use, like, repetitively, you know, it'll have a 15,000th radius. And then I'll have another returning tool that has a 32. Right? Yeah, it kind of keeps things, I don't know. Sometimes you need a 15,000, sometimes you need a 32. 15,000 is better at breaking the shavings, and you'll get a nicer surface finish. 32 will last longer, especially if you're cutting abrasive materials or even like stainless steel, where tool wear becomes excessive. You know, a bigger radius definitely helps for tool life. So, so like on the insert shape, for example, the symbol, you have letter symbols. All right, so H is for hexagon, O is for octagon, P is for pentagon, C is for rhombic 80 degrees, D is for the 55 degree, E is for 75. Most of the time, the most common sizes you're going to see is like an 80 degree, let's see, an 80 degree, a 55 degree, and a 35 degree. And like a triangle insert. I don't know, we don't use too many hexagon or octagon, not on the lathe. You'll see a lot of triangular inserts. Okay, so we got insert shape, we have tolerance class. Then you got different types of chip breakers, insert size. Basically, usually what you do is, this is a CN LMG. So on a CN LMG, you know, so this would be your C, which is already on there. And I have N, M, and instead of a T, this is going to be a G right here. This is the tolerance class right here. So you have like your width, then they have this IC diameter. Basically, you know, your inserts have a labeling, you know, chart that they use. Okay, so CNMG, basically, you're gonna fill in for your shape, the relief, the tolerance, and the cross section. Okay, the insert thickness, that's gonna be a 3. and the insert size, I think they call it the inscribed circle. That's what IC is, inscribed circle. But anyways, that's what this is right here. Okay, basically, if it made a circle for, you just look at this imaginary circle we have right here. That's what, that would be 0.38 right there. And that looks about right. I don't know why the thickness came up as 0.38. This would be a number 3. And corner radius, we'll say 0.015. It's not exactly 15 thousandths, but it's close enough. Okay, so the holder geometry, I really wouldn't worry about this. You really don't have to get all this information. The only thing that you really have to make sure you have right is this corner radius, okay? This will affect your G-code. Now, depending on what you're doing, what kind of toolpaths you're creating, this other stuff may not affect your G-code too much. And while I'm saying affect your G-code is if you write a program and you don't use that insert, does the part still come out the same? And usually yes, okay? Unless in some cases, say you use the square insert, the distance it fed back in the Z direction, basically if you had like a 9-degree shoulder, it may not be 9 degrees. It may be a different angle. But usually, this is a pretty standard insert. So usually if you just get this number right here, in most cases, as long as this corner radius is right, you should be good to go. The G-code will be fine. Okay, so if you say you program chamfers and the chamfers aren't actually coming out on the part, that could be some kind of conflict with your corner radius settings. So keep that in mind. Holder, we'll just leave that default. Setup orientation, by default this should come out right. Okay, now when you start boring and doing stuff like OD grooving and ID grooving, this page may not come up default in the right orientation. You'll have to change it. But just say general face and OD cut tool, yeah, the orientation is going to be right. Cutting data, so these usually have some kind of ranges that you can work within. Now there's more to it, depending on what material you're using. This right here, your surface speed can be anywhere from like 950 to like 1150. I think by the book for basic steel, carbon steel, I think it's like at 1150. I found on my machine running it at 950 actually works better. On stainless steel, I've seen people go as low as like 250 or 350 surface feet. Okay, that's not RPM. It affects your RPM, but it's not your RPM. It's your constant surface speed. Okay. I'm not sure if everyone knows what constant surface speed is, but basically, instead of calculating your spindle speed by RPM, revolutions per minute, basically what it does, it's the amount of material that travels across the tool. Okay, so say that you have a 8-inch part in your chuck. If you were to unwrap that 8-inch, if it's an 8-inch diameter part, it's round, right? If you were to unwrap it where it was straight and flat, that distance would be the distance that travels across the tool interface per revolution. Okay, now say we'll just say it's what 12.1 inches or something, right? So in 1 minute, basically you would have 1 foot point, it's 12 inches point one, that would travel across your tool interface. Okay, so instead of revolutions, every time it made a full circle per minute, you're actually calculating how much surface feet travel across the cutting edge. All right, that's what the difference is. Cutting feed rate per revolution, by the book, 12 thousandths is standard for roughing on a lot of materials. Depending on the hardness of the material, you maybe will go faster or slower. And it's your tool number. One thing you want to watch out for on the lathe is make sure that your maximum RPM here isn't too fast. 5,000, probably fine for a small part. Now, if you have a part that's over 3 or 4 inches in diameter, I would not want to be going 5,000 RPM. Typically, the larger the diameter, the slower you're going to go on RPM. Alright? Now, it's not calculating the speed by RPM, but there is a set RPM, like a maximum RPM you can reach. Okay? The reason why it has to have both of these. That's because if you're traveling 950, depending on how far you're out on the X, this is going to speed up or slow down to maintain a 950. Now, as you get closer to the center, what you'll see is the spindle will start speeding up faster and faster to maintain 950 surface feet traveling across the tool interface. Okay, so you're going to quickly meet your maximum RPM as you get closer to the center of the part. So it's a good idea to have a maximum RPM. Actually, I think you have to have a maximum RPM. The machine may not even. It may throw an alarm if you don't have a maximum RPM. But small parts, you can go fast. The larger diameter parts, or really long parts, you want to slow it down some, because the parts will start to whip in the machine, and basically, the faster it goes, it'll start to deflect from the torque or the rotational speed, and you'll start to see it. A lot of machines call it whip. Basically, it'll kind of whip back, and it'll actually flex the material, and once it flexes the material, it'll start whipping even more, and eventually I've seen it happen before. Somebody put some material that was too long in the machine for the RPM, and the machine turned on. It was like half inch diameter material. It was only sticking out of the machine like this far, probably. And they turned the machine on, and I was sitting there talking to them. And what happened is one of the saw guys got some material mixed up, and basically there was some material that was a little bit too long. I mean, it was only like 6 inches too long. It got put with the lathe to get run, loaded into the machine, and ran. So when the spindle turned on, it created like a whipping action, and basically, it turns on and it does this, and from the force of it, it just bent the material and once it did that, the machine started moving and started walking, and the machine was literally walking, the lathe. And to go hit the emergency stop, because it was me and one of the guys, and he was by the control panel, and I was on the other side, of the machine, and then once the machine started walking, it was unsafe for me to walk in front of the machine that's walking towards me, to hit the e-stop. But I mean, he hit the e-stop button, but it happened really quick, man. we're just sitting there talking, running the machine, you know, and he put a new part in there and hit cycle start, and all of a sudden, the machine just started. I mean, the material just bent. You know, as soon as that spindle turned on that fast, the material just deflected into a complete 90 degrees. And I don't know if you ever thrown shoes into a dryer, and the dryer will walk. It was like that, but like times 10 on a CNC lathe. You know, it. Yeah. But anyways, be careful with the maximum RPM because you can get yourself in trouble by going too fast. I mean, even at the school, I would be careful because say you have a piece of 1 inch bar, you know, and it's sticking out this far without a tailstock. You know, if that spindle turns on 5,000 RPM, that material is gonna deflect and it's gonna kind of whip and deflect. And you know, once that happens, you know, think about it this way: you have a bar material this long sticking out from the chuck, right? If you turn the spindle on and it deflects and whips back 90 degrees, then you have this spinning mass that's sitting there spinning. It could tear the machine up. I mean, you could possibly destroy that lathe that's in the shop by going too fast. All right, so just be careful. Not trying to scare y'all, but it's definitely something you want to watch out for. Okay, so yeah, we'll bump this down to 3,000. Here, I know I was kind of talking. I'm gonna start over on that. Okay, so I got this set up. So the first thing I'm gonna do is face the part. So I'm gonna select that tool that I just created a minute ago. So I'm gonna select that. We'll bump the maximum RPM down some. And I can also change that in the tool settings too. So by default, that comes up a lower number. So the next tab is the geometry. You know, so you just want to select the face of the part, which is usually the model front. I would suggest using the model front. Then you have the radii of the part. The way Fusion works now, you used to have to actually enter all these values and tell the software, you know, how to run it. Nowadays, you can literally just hit OK. Okay, they put everything so by default the settings are right. Now, the only thing is, say that you have 100,000 to face off. Well, it just took that material in one pass, which may be too much of a load for that tool, you know. Whoa, hold on. What's going on here? Alright, so when I hit simulate and play, notice where my tool's coming back. Yeah, so if y'all have this problem where the tool is actually coming from back here, I guess on the newest update, I've seen they've always had this option on here. I mean, it could have been me. I could have accidentally selected that. I had it on stock back. It needs to be on stock front. WCS origin should work the same as stock front. That's because our origin is right here. Here, let's check it out. Yeah. But anyways, for future reference, on your setup, your safe Z reference, don't put that on stock back. I don't know if I accidentally clicked stock back or that was the default setting, but y'all saw what happened. Okay, so sometimes you're gonna want to take, if you look at this face pass, it's just taking one pass, right? Sometimes that's going to be too much for your tool to handle, or one pass, your surface finish isn't going to look that good. So what you could do is on your passes tab, put this on multiple passes, and 40,000 step over is good. That's a good value. And now it takes 2 passes. Alright. And okay, so is that setting that we just changed to multiple passes? Now how did it calculate 2 passes? Because we didn't tell it to take 2 passes. We told it to take 40,000 step over. There's no spot to tell it how many passes to take. Well, what it's doing, it's calculating on the setup for the stock. It's calculating the distance in front of the part, right? So this distance from here to where the stock starts, that's 100 thousandths. Or is it? Hold on. No, it's 50 thousandths. Whatever number. Okay, so say, just for the fun of it, say I put this to 1 inch. Okay. So right here, I have 1 inch to face off. So if I regenerate this toolpath, what you're gonna see is this. So now it has a bunch of passes, right? So that's how it's calculating how many passes it to take. It looks at how much stock material you told that's in front of the part, and how many passes, like we tell the step over distance. So it takes the stock that's left, that needs to be faced off, and divides that by 40 thousandths to calculate the number of passes. But anyways, I'll change that back. Probably 0.05, or Garrett's probably gonna want y'all to put like 100 thousandths on there, and that's a good number. But after you change that value, you have to regenerate the toolpath so it can recalculate. And in this case, with 100 thousandths, it's gonna be 3 passes there. Okay. So that's the face. And, I kind of went over everything in a lot of detail. I mean, to keep it simple, say I delete this face, so I don't have it, right? Literally, all you have to do is go to turning face, select your tool, make sure your maximum RPM isn't too fast. In all reality, you could just hit OK. I would put it on multiple passes, and that's it. Like, that's all I had to do. I changed like 3 things. The OD is pretty simple. I'm gonna use the same tool. Maximum RPM. Now, if you look, when I open up, alright, when I go to create a turning or a profile roughing, oh well. Alright, so So I'm gonna do a profile roughing, which is an OD cut. It could be used for ID. You know, you would change it. Right now it's set on outside profiling. If I was like boring and using a boring bar, I would put it on inside. But I'm not, so I'm gonna have this on the outside. We'll bump that RPM down some. Just for the sake of the lesson, I'm going to leave a lot of this default and show you the toolpath it gives us, and then show you how to modify it. Let's see. I can literally hit OK, and it's going to give me a toolpath. Now, it may not be perfect, which it does look pretty good. That actually doesn't look bad at all. Well, we are. Well, I mean, we got 20 inches actually. I mean, okay, so this is assuming that you're gonna part it off. Okay, so at the school, y'all usually run one part at a time. Think about it this way. So in the machine shop scenario, you're trying to reduce waste, and if you saw a piece of stock off, but it's an inch long, you're gonna have more waste, okay, than if you leave it on the bar. Usually, what you do is on the spindle of the machine, they're usually 20 inches, 24 inches. It depends on what machine you're using. Usually what you do is you cut a bar that goes all the way inside that spindle, right? So when you go to part it off, you're holding on to the stock, right? To that bar. Now if you cut this an inch longer, then that kind of makes things more of a pain, really. It would look something like this. Now I gotta be honest, you know, I'm just telling y'all how you would do it, like in a machine shop. Like the way y'all do it in class may be different because it's a different context, you know. You know, the school's gonna be a lot different than a real machine shop, because in a real machine shop you're trying to make money. You know, in the school, they're trying to make sure you learn. You know, but this is how you would do it in a shop. You would actually have, you know, your whole stock bar in there. And so this still needs to be part off, right? So you could do is we go to turning part, and y'all probably don't have a part off tool, so we'll go ahead and make one. Well, we'll just go through the process. So on turning, it doesn't actually have a cutoff tool, but if you if you think about it, what is a cutoff tool? It's pretty much a long grooving tool. So we're going to select grooving,